In this video, I want to have a look at integrating exponential functions. So we know from our earlier videos that if we differentiate e to the x, we just end up with e to the x. So the function hasn't changed, it is its own derivative. So the reverse is true as well. If we integrate e to the x with respect to x, then we end up with e to the x, and because it's an indefinite integral, we also have that constant term added on the end. If we have a look at functions that are slightly more complicated, the integral of e to the ax plus b with respect to x would be 1 over a with that same exponential, so e to the ax plus b plus that constant. So the exponential stays the same, but we divide through by the derivative of that power. So this one here is on your formula sheet that you get in every exam. So let's have a look at some examples. We're asked to evaluate the following integrals. So our first one, we've got the integral of 2 minus x plus e to the x with respect to x. So we're going to go through and integrate each term. So our 2 will become a 2x, our x will become an x squared over 2, and our e to the x will just stay as an e to the x. And because it's an indefinite integral, we have to add our constant on the end as well. Right, our second question, we've got e to the power of 4x plus 1. So that exponential stays the same, e to the 4x plus 1, oops. And then we divide by the power, the derivative of power, which would just be 4. So we can write it as divided by 4, or we could write it as 1/4 e to the 4x plus 1. Either way is correct. And then we need our constant term on the end as well. Our next one is a definite integral. So integrate between 0 and 1, 2 e to the x dx. So integrating that, our 2 doesn't have any effect, so that's still just going to be 2 e to the x, but we've got our upper and lower bounds that we need to substitute in. So we would have 2e to the power of 1, which is just 2e, minus 2e to the power of 0, but e to the power of 0 is just 1, so we'll just end up with a minus 2. All right, our fourth example is the integral from 1 to 5 of e to the 3x minus 2 with respect to x. So again, it's a definite integral. Now this one, we're going to have e to the 3x minus 2, and we're going to have to divide by 3. So dividing by the derivative of that power, and then evaluating that from 5 to 1. So substituting those in, we would have e. If we sub this 5 in up here, we'd have 3 times 5 is 15, minus 2 is 13. So we'd have e to the 13 over 3, minus, and then e to the 1, substituting 1 in there, we'd have 3 times 1 is 3, minus 2 is just 1, so we would have e over 3. So we could simplify that just into one fraction, so e to the power of 13 minus e all over 3. So our next example is a little bit different. It says if our first derivative of a function is e to the 3x minus 1 plus 2, we want to find the original function if we know that f of 1/3 is equal to 1. So if we've got f dash of x equal to e to the 3x minus 1 plus 2, then our original function will be equal to the integral of that. So we're going to integrate that whole thing, and then we can use this extra piece of information to help us figure out the exact function. So integrating this, we would have e to the 3x minus 1 over 3 plus 2x plus c. So this is a whole family of functions at the moment that would differentiate to give this. So we need to find the exact function, and we can do that using this extra piece of information. So we have f of 1/3 would be equal to, so we're going to substitute a third into this. So e to the power of 3 times a third is just 1, and 1 minus 1 is 0, so this whole numerator will just become 1. So we'll have 1/3 plus 2 times a third, which would be 2/3, plus c. Now we know that this whole thing has to equal 1. So a third plus 2/3 is 1, plus c is equal to 1, which means that c has to equal 0. So our original function will be f of x equals e to the 3x minus 1 over 3 plus 2x, and because our c was 0, that's it. That is our original function. Our last example has two parts. First, it asks us to differentiate e to the power of x squared. Then it asks us to evaluate the integral of x e to the power of x squared with respect to x. So let's have a look at this first bit. So we have, let's just call it y equals e to the power of x squared. And if we differentiate that, we would have the derivative of the top, so 2x, multiplied by the original function, so e to the power of x squared. Now we can use this to help us evaluate this integral. So we've got the integral of x e to the x squared dx. So this is very similar to this derivative that we've got here. So we've got that x e to the x squared that we need, but we also have this 2 here. So we're going to manipulate this to look more like this one. So we want it to be the integral of 2x e to the x squared, because we know that's going to integrate back into this original function that we had. But if we introduce a 2 here, so if we multiply everything by 2, we have to compensate for that. So we're going to put a half out the front as well. So we've got half times the integral of 2x e to the power of x squared. So now we know how to integrate this because we can just do the reverse that we did here. So we're going to end up with a half e to the x squared, and we need to add our constant on as well. So that's an introduction to integrating exponential functions.